Download this code from codegive.com, link in the description below. OK, let's dive deep into the cascading problem that can occur with dynamic CMOS logic, specifically the charge sharing issue, its impact on output accuracy, and how to mitigate it. We'll cover the theoretical background, a code example in SPICE, though the principles apply to any circuit simulator, and best practices for designing robust dynamic logic circuits. Understanding dynamic CMOS logic. Dynamic CMOS logic relies on the temporary storage of charge on the parasitic capacitance of a circuit node, typically, the output node. It's a powerful technique often used in high-speed, low-power digital circuits because it generally requires fewer transistors than static CMOS logic for the same function. Key elements precharge transistor, pmos. During the precharge phase, clock is low, this transistor turns on, pulling the output node to VDD. The output capacitance is charged to a logic 1. Evaluation network, NMOS pull-down network consists of NMOS transistors arranged to implement the desired logic function. During the evaluation phase, clock is high, this network potentially discharges the output node to ground, logic 0, depending on the input signals. Clock signal controls the precharge and evaluation phases. Advantages higher speed typically faster than static CMOS due to reduced transistor stacking and lower input capacitance. Lower power consumption no static current flows when the circuit is in the evaluation phase, ideal case. Power is primarily consumed during the precharge and discharge transitions. Smaller area fewer transistors are needed for complex functions. Disadvantages charge sharing this is the main problem we'll focus on. It can cause the output node to discharge incorrectly. Clocked operation requires a clock signal, which can increase design complexity. Charge leakage the charge on the output node can leak away over time, leading to incorrect output. This requires a high enough clock frequency. Noise sensitivity more susceptible to noise than static CMOS. Not easily cascadable direct cascading of simple dynamic gates is problematic without careful design considerations. 2. The charge sharing problem. Charge sharing is the phenomenon where the charge initially stored on the output node, COD, is redistributed among other internal capacitances within the evaluation network, example the capacitance of intermediate nodes between transistors. This redistribution can significantly lower the voltage on the output node, potentially causing a logic 1 to be misinterpreted as a logic 0. How it happens 1 Precharge the output node, COD, is precharged to VDD during the precharge phase. The internal nodes of the evaluation network are initially discharged to ground, or have a voltage determined by their previous state. 2 Evaluation the clock goes high, and the evaluation network becomes active. 3 Conditional discharge if the input conditions are such that the pull-down network should discharge the output, the following occurs. The output capacitance COD begins to discharge towards ground through the active NMOS transistors. Simultaneously, the internal capacitances, SINT, within the pull-down network also start to charge up. Charge is shared between COD and the internal capacitances. 4 Problem if the ratio of the internal capacitance, SINT, to the output capacitance, COD, is large enough, the final voltage on the output node after charge sharing might be significantly lower than VDD and could even fall below the threshold voltage, VTH, of subsequent gates, leading to a faulty logic 0 being registered. Mathematical explanation Imagine COOT is initially charged to VDD, and SINT is discharged to 0. Let's simplify and assume only one internal capacitor SINT exists within the NMOS network. Initial charge on COOT, CO equals COOT VDD. Initial charge on SINT, KINT equals SINT 0 equals 0. Total initial charge, total equals CO plus KINT equals COOT VDD. After charge sharing, the final voltage, V final, on both COOT and SINT will be the same. The total charge is conserved. Total equals, COOT plus SINT, V final. Therefore, COOT VDD equals, COOT plus SINT, V final. Solving for V final. V final equals VDD COOT plus SINT. This equation clearly shows that if SINT is significant compared to COOT, V final will be much less than VDD. When is charge sharing a problem? Large internal capacitance, SINT long chains of transistors in the pull-down network or complex logic functions increase SINT. Small output capacitance, COOT. If COOT is small, the effect of charge sharing is amplified. This can happen when driving small loads, few subsequent gates. Low supply voltage, VDD. Reduced VDD makes the voltage margin smaller, making the circuit more susceptible to charge sharing problems. 3. Dynamic logic cascading problem. Directly cascading dynamic logic gates can cause significant problems. The issue arises because the output of a dynamic gate is only valid during the evaluation phase. If you directly connect the output of one dynamic gate to the input of another, the second gate might start its evaluation before the first gate's output is stable. This can lead to incorrect operation and potential signal race conditions. In addition, there can be a glitching when cascading two dynamic logic gates. Let's elaborate with some more examples. Direct cascading issue Precharge phase The outputs of both dynamic gates are precharged to a high voltage, VDD. Evaluation phase The evaluation of the first dynamic gate, gate 1, depends on its inputs. If the pull-down network of gate 1 is activated, its output will start to discharge towards ground. Race condition The output of gate 1 is the input to the second dynamic gate, gate 2. However, gate 2 also starts its evaluation phase simultaneously. Gate 2 might start to evaluate before gate 1's output has completely settled to a low voltage, if the pull-down network of gate 1 is active. This can cause gate 2 to evaluate incorrectly, as it might interpret a partially discharged output from gate 1 as a high voltage, logic 1. Incorrect logic Consequently, the overall function implemented by the cascaded dynamic gates will be incorrect. Monotonicity requirement Dynamic logic gates require monotonic inputs during the evaluation phase. This means that the inputs to a dynamic gate should only make a single transition, either from low to high or from high to low, during the evaluation phase. If the inputs to a dynamic gate are non-monotonic, the output might be corrupted due to the temporary storage of charge on the output capacitance. This condition can be violated when cascading. Glitching issue. Cascading to dynamic logic gate can cause glitching. The glitching is caused by the finite transition time of the first gate, that will drive the second gate. Due to the finite transition time, the second gate might start to evaluate with a partially evaluate input, that causes the glitching. 4. Code example, SPICE, illustrative. This example demonstrates charge sharing and the cascading problem in a simple dynamic NAND gate circuit using SPICE. The principles are the same for other simulators. Explanation The code simulates a dynamic NAND gate, gate 1, and a simple inverter, gate 2, with charge sharing effects. Sint represents the internal capacitance, and it is connected to outint node. The simulation plots the voltages at the output node, out, the internal node outint, the output of the cascaded gate out2, and the input signals A, B, C, Lk. Run the simulation. You should observe that the output node is not fully discharged to the ground, because of the internal capacitance Sint. Also, observe that the second gate output is not correct, the glitches on the first gate output, propagates to the second gate output. Play with the value of Sint and the transistor sizes to notice how charge sharing affects the output voltage and cascading problems. Techniques to mitigate charge sharing and cascading issues. 1. Increase output capacitance, COUD. By increasing the COUD, you effectively reduce the impact of the Sint. This can be achieved by increasing the size of the output transistor, if it's driving another gate, or by adding explicit capacitors to the output node. However, increasing COUD can also increase the switching time of the gate and power consumption. To minimize internal capacitance, Sint. Reduce transistor stacking. Try to reduce the number of transistors in series within the pull-down network. Complex logic functions often require long chains of transistors, which increases Sint. Restructuring the logic function or using alternative logic styles, example pass transistor logic, might help. Reduce wire length. Keep the wiring within the gate as short as possible to minimize parasitic capacitance. Minimize diffusion capacitance. Use minimum sized transistors where possible, while still meeting performance requirements. 3. Precharge internal nodes. Precharge transistors. Add pmos transistors to precharge the internal nodes of the pull-down network to VDD during the precharge phase. This eliminates the charge sharing problem because all nodes are initially at VDD. This approach comes at the cost of increased transistor count and potentially higher power consumption. 4. Domino logic. This is the most common and effective technique for cascading dynamic gates. It uses a static CMOS inverter at the output of each dynamic gate. How it works. 1. The dynamic gate behaves as described before. 2. The output of the dynamic gate is fed into a static CMOS inverter. 3. The output of the inverter is then used as the input to the next domino gate. Benefits of domino logic. Monotonic inputs. The inverter ensures that the input to the next dynamic gate is monotonic, only transitions from low to high during the evaluation phase. This prevents spurious switching and improves robustness. When the previous stage's evaluation is complete, the input to the next dynamic gate transitions from low to high only. Cascadability. Domino logic allows for easy cascading of dynamic gates because of the monotonic input property. Improved noise margin. The inverter amplifies the output signal of the dynamic gate, providing a better noise margin. Drawbacks of domino logic. Increased transistor count. Adds an inverter to each gate, increasing area and power consumption. Inverting logic. Domino logic implements inverting logic functions. To implement a non-inverting function, you need to add another inverter, further increasing transistor count. Clocked operation. Still relies on a clock signal. Single-phase clock. Requires a single-phase clock. 5. Keeper transistor. A small pmos transistor connected between the output node and VDD can help to maintain the voltage on the output node during the evaluation phase, especially in the presence of charge leakage or noise. The keeper transistor is usually sized very small, so that it doesn't interfere with the pull-down network. Asterisk how it works asterisk. Asterisk the keeper transistor is weakly on when the output node is high, VDD. It provides a small amount of current to compensate for charge leakage or the effects of charge sharing. Asterisk during evaluation, if the pull-down network discharges the output node, the keeper transistor is turned off. Asterisk it counteracts charge leakage and helps maintain the output voltage at a valid logic level. Asterisk drawbacks asterisk. Asterisk contention asterisk if the keeper transistor is too strong, it can contend with the pull-down network, slowing down the discharge process. Asterisk power consumption asterisk the keeper transistor consumes a small amount of static power. 6 charge sharing compensation circuits asterisk advanced techniques involve adding circuits specifically designed to compensate for charge sharing. These circuits can detect when charge sharing is occurring and inject additional charge into the output node to maintain the correct voltage level. 7 circuit simulation and verification asterisk thoroughly simulate your dynamic CMOS circuits using SPICE or other circuit simulators. Pay close attention to the voltage levels at the output nodes and internal nodes to identify potential charge sharing problems. Use worst-case process, voltage, and temperature, PVT, conditions in your simulations to ensure the robustness of your design. 6. Best practices for dynamic CMOS logic design. Asterisk minimize logic complexity asterisk keep the logic functions implemented by individual dynamic gates as simple as possible. Asterisk use domino logic for cascading asterisk this is the preferred approach for most applications. Asterisk size transistors carefully asterisk optimize the transistor sizes to balance speed, power consumption, and charge sharing immunity. Asterisk use a keeper transistor asterisk add a keeper transistor to the output node to prevent charge leakage and maintain the output voltage. Asterisk thorough simulation asterisk simulate your design under worst case conditions to identify potential problems. Asterisk consider process variations asterisk account for process variations in your simulations to ensure that your design is robust. 7. Advanced dynamic logic styles. While domino logic is the most common solution to the cascading problem, there are other more advanced dynamic logic styles. Asterisk zipper logic asterisk uses alternating N-type and P-type domino stages to achieve non-inverting logic functions without requiring an extra inverter. Asterisk NP domino logic asterisk combines NMOS and pmos dynamic logic stages. These advanced styles can offer advantages in specific situations but are generally more complex to design and analyze. 8. Conclusion. Charge sharing and cascading problems are significant challenges in dynamic CMOS logic design. Understanding the underlying causes and using the appropriate mitigation techniques are essential for creating robust and reliable dynamic circuits. Domino logic is a widely used solution, but other techniques, such as precharging internal nodes and using keeper transistors, can also be effective. Remember to simulate your designs thoroughly to verify their correctness and robustness. By following these best practices, you can harness the advantages of dynamic CMOS logic while avoiding its pitfalls.